our class and continue with what we're doing. Okay, so we're still on the complex numbers, whereby a lot of us were having problems on how do we solve certain variables, right? So for example, we're dealing with example 1.4, whereby we're having find the polar coordinate of z is equals to 1 plus j. So the first thing that we said we have to do was to create a sketch. So we did create a sketch, and we had some other colored a diagram that we're now referring to. So whilst it's still there, there are certain things that you just have to remind each other, just a little bit, not a lot, but just simple things that you have to remind each other on that point. So we know that whenever we're having an equation that needs to be resolved, the first thing that you have to do, there are certain steps that you have to follow when you're dealing with complex numbers. Okay, so let me just show you these steps. Like, for example, let's say we're having we're going to have something like 3 plus, like 3 plus, we use 3, so let me change to 5 plus 7j. Okay, so we have this variable here, then we need to change these things to polar form. Okay, so we have to change this to what? To polar form. Okay, for us now to be able to change this to polar form, there are certain things that you have to do, because you understand that this thing, when it's like this, we're having what we call a rectangular form. This is in a rectangular form. This one is called our rectangular form. Rectangular form. Okay, now for us to convert here, of course there are two methods. So the first method is by using a calculator, and most of us, unfortunately, we don't have the calculators at the moment, but as we get the calculators, there is a very simple way to actually get to convert any complex number that we're given from any variable that you are having towards to the polar form. But now, before break, we're having something like, let's say, for example, when you're having this one, we're using the diagram method. So we're going to apply the diagram method. We're going to apply what we call the diagram method here. Okay, so when you're applying the diagram method, we're saying we have a diagram like this. We're having a diagram like this, then also like this. So we understand that from the diagram we're having the y-axis as well as the x-axis here as well. So this is our x-axis that we're having here. We're having our x-axis. So we're having our x-axis on this end, and also having the y-axis. So now we remember that, or we can just like try to recap on the fact that on the x-axis, when we say we're having the variables that are on the axis are what are our imaginary variables. So here we're having the imaginary numbers only. So the imaginary numbers consist also of the likes of the imaginary numbers consist of complex numbers. So we know that on this diagram, guys, on the right side here, we're having what? Positive. And on this side is what is negative along the x-axis. Then the y-axis, the upper part is positive. Then the lower part is what? Is negative. Okay. So now the first thing that you have to do, you have to check now the variables. On this case, we're having 5 plus 7j. So now if it's 5 plus 7j, what we have to remember now is that 5 is positive and 7 is what is positive. So everything that we're having is supposed to be within this what first quadrant. So what we're just going to do is we are going to draw a straight line like this. Then along that straight line, you're going to now label it. So we're just going to have like this, then also this. So we are saying this one, which is the imaginary, is going to be now our 7j, and this one, the real line or real axis, you're going to have the what? The 5. So now, when you're having these two variables that you have placed here, we have completed the what? The diagram. But now remember, we haven't changed this thing from what? From rectangular form. This is rectangular form to what? To polar form. So now how do we convert that? The first thing now, number one, is to what? Calculate. We have to calculate our angle theta. So now to calculate angle theta, we're going to say tan theta is equivalent to what? Opposite over adjacent, like this. So the reason we are saying that is that this one is called the opposite. Why is it called the opposite? It's called the opposite because it's on the opposite side of the what? Of the angle. And this is the adjacent because it's where the angle starts before it gets to the what? To the hypotenuse. So now we're going to say now our tan theta is equivalent to opposite. Now we are dealing with units. So whenever you're calculating this angle, there's no need for you to now use the j's because we are dealing with units. You're saying from this point here to this point, we're having 7 units. And also from this point going upwards, we're having what? 5 units. So we're saying opposite is going to be 5 over what? Over 7. But our main focus on this one is not to calculate tan theta, but we need to get the angle what? The angle theta. So now to get the angle theta, we're going to use the formula. Theta is equals to tan inverse of open bracket 5 over 7, like this. Meaning that now our theta, if you punch our calculators now, with the calculator, I still remember telling you guys or showing you guys how do we do that with the calculator. So we're going to say 5 dividing, let me just do this here, or times 0, so that I get the answer. 5 divided by 7, then I get this one, second function, tan. So I'm going to get something like 35.538. So I am having 35 point degrees. So this is the answer that I'm supposed to get at the first end. But now, even if I have the theta, I have this line. I have this line from here to here, and I also have this line from here to here. But now the problem is we do not have the length of this line here. So this line, we call it what? Our R, which is also called the modulus. So what we're going to do now is that we're going to say R is equals to the square root of what? Of x squared, or x unit squared plus what? Y units squared, which means that our R is equals to the root of x squared. We are saying that's 7 squared. That's going to be 7 squared plus our Y is what? 5 squared. So at the end of the day, we are having something like, if we are to punch our calculators, we know that it's going to be now 5 squared plus 7 squared is equals to 74. Then we need the root of that. So it's going to be now root of 74. So this is going to be our answer. But now remember, the main focus of this was not to calculate only these two things, but was actually to change this rectangular form to a polar form. So your answer now, your final answer will be equal to Z is equivalent to, sometimes you find that it is not an array at the top, so it's going to be Z is equivalent to root of 74 CIS 35.538 degrees, meaning that which is equivalent to root of 74. Then we have this thing as 35.538. Okay, so basically that's all about how to deal with these diagrams. Okay, so when you're at home or wherever you are trying these things, may you please just like try to do the following questions. I know it might be a bit tough, but don't be afraid to reach out to me if ever you have problems. So we are saying number one, may you do Z is equals to 7 plus 8J. Number two, I want you guys to do Z is equals to 3 plus 5J. So here I want you guys to change these from rectangular form to polar form. Okay. So now we can move back here and we actually check the other equations. For example, here you can see that, right, Z is equals to 2 plus 3J in CIS form. So CIS form simply means that we are converting that thing to a rectangular form. From rectangular form to polar form. So not that Z is equals to -2 and 3. Where are they getting these things of -3 and 3 is in the sense that I just want to try to enlarge this. How is going to be possible? Can't. So here on the question, you can see that Z is equal to -2 plus 3J. So if it's -2, -2 is this side. So I remember on the Cartesian plane, I said that positive is on the left along the x-axis. So now we're saying on the x-axis going to the left, you're going to have -2. Then on the y-axis, you're going to have 3. So now the first thing that we have to do here is to calculate the auxiliary angles, which is also called sometimes the modulus or the module. So we are having theta is equals to tan inverse of what? Of the unit. So it's going to be theta is equals to tan inverse of what? 3/2. So here there's no need for us to write -2 because we only consider the units. We don't consider the variables that you're having. So it's going to be now theta is equals to tan inverse of 3/2. Then we get this 56.309 degrees. Now, looking at the sketch, theta is equals to 180 degrees, then whatever, minus alpha, then we get that one. Okay, so they just wanted to get the other angle at the other end. But now to get the r is going to be now equivalent to -2 squared. You can even use 2 squared because we are dealing with units, we are not dealing with numbers. So it's going to be -2 squared plus what? 3 squared, then you're going to get root of 13, which is equals to 3.61. Working with complex numbers, okay. So we have what we call the Morph theorem, which is use the polar form of complex numbers to find the product, quotient, and power of complex numbers. Okay. So we are having let Z1 is equals to R1 theta 1 and Z2 is equals to R2 theta 1. So sorry, theta 2. Whenever we multiply different what they call it, complex numbers, we're going to say Z1 multiplied by Z2 is equals to R1 multiplied by what? R2, which is equals to Z1 times Z2 is equivalent to R1 multiplied by R2, open bracket, theta plus theta. So here, what we are trying to say is this. Let me just try to write this thing down. We have something like we're saying Z1 is equals to R1 theta 1 and Z2 is equivalent to R2 theta 2, right? Something like this. So now to get Z1 multiplying Z2, we're going to have R1 multiplying R2, then open bracket or something like this, theta 1 plus theta 2. So these are basically formulas that we're going to be using whenever we are dealing with with complex numbers, is basic theorems or basic formulas. So here we're having, whenever I have multiplication, we're going to use this, and whenever I have division, it's subtraction. Then powers in complex is going to be R1 to the power of n, then you have n theta 1. Okay, so whenever you're practicing, I would advise you all guys to go back and actually check on page number 14 of these slides that I've created, and actually are going to see all the formulas that we need. Okay, so here we have an example that I've created. If Z1 is equals to 2 slide of 30 degrees and Z2 is equals to 3 slide of 40 degrees, find Z1 multiplied by Z2 and Z1 divided by Z2. So now we are saying Z1 was given as 2 30 degrees or 2 upon 30 degrees. So what we are going to do is that Z1 multiplied by Z2, we multiply the R's, which is the radiuses. So we're going to be 2 times 3, then we open the bracket 40 plus 30, meaning that it's going to be 60. So it's going to be 6 CIS 70 degrees. And Z1 over Z2, here we're just going to say 2 over 3. Then we are going to subtract our powers. Okay. So when you are at home, guys, remember this is mostly of self-study, so we have to actually get into deep with it and study these things as much as you can. Okay. Now we go to the phasor representation, which is the frequency and speed. So they're saying both the sinus and cosine wave forms here have the same form in the cycle of 360 degrees. The difference between the two is that the cosine wave form is moved by 90 degrees before the sinus wave. This means that the cosine wave reaches its maximum value at 90 degrees before the sinus wave does. So this is basically like when you're talking about frequencies. Whenever we're having a sine wave, a sine wave is always going to be following the cosine wave, and also the cosine wave is going to be ahead. Okay, so let me just I'm seeing a hand there. Yeah, Mr. You can talk. Yeah, Mr. Stella.
Hello, sir. Hello, sir.
How are you, man?
I'm good. I don't know if it's from my side or what. I don't know if maybe like you're not sharing the screen, or maybe it's from my side. I don't know.
Yeah, I think maybe it's your network, but let me just cancel first, then I'll say again to check if it's gonna change. Let me start again. Okay, so I've shared again. So you might be able to see it now. I don't know if you're seeing it. Are you able to see it now?
No.
Oh, I think it's your device maybe, because this side I'm sharing it. Maybe it's network. But I'm going to share this recording, so you also be able to check it out when I share it. Okay, so here I was saying the sine wave is going to be ahead of the cosine wave at time, but now to reach the maximum value is going to reach it before the sine wave. Okay, so we're saying fig 1.10, a waveform diagram of sinus and cosine wave forms. The sinus wave begins with a value 0 at 0 degrees, 180 and 360 degrees, and reaches a peak value of 90 degrees and maximum value of 270 degrees. Whereas the cosine wave begins with a peak value of 0 degrees and has a peak of 360 degrees. The wave crosses the zero line at angles of 90 degrees and 270 degrees with a maximum and with a minimum at 180 degrees. Okay, so a cycle can be seen as that part of the waveform before it starts to repeat itself. In the case of sinus wave, this is the part of the signal oscillating to a maximum on the positive side of the time axis, then back to zero on the maximum negative and back to zero line. Then we have something that we call the phase angle. So whenever we're talking about the phase angle, we're saying the phase angle, the angle with which the current leads or lags the voltage. So basically that's a phase angle. So in practice, the current leads or lags the voltage by a small angle. This angle is referred to as the phase angle theta, or which is phi. In most cases, the current lags the voltage is shown in Fig 1.10. So we're having that before here. We can see this one, whereby another a wave is being lagged by what? By another lag. So in pure resistive circuit, the current is in phase with the voltage. Then we have what we call the phasor. A phasor is a complex number representing a sinusoidal function whose amplitude A, angular frequency, and initial phase theta are time invariant. If it decomposes a sinusoid into the product of a complex constant and a factor that encapsulates the frequency and time dependence. The complex constant which deals with this thing is known as the phasor or complex amplitude. Okay, so for you to really understand these things, you have to actually also go back into the basics of this and actually read through the notes. When you are reading through the notes, you also make your own notes. So at the end of the day, when you have everything that you need, you can now go to the TVET question memos, then you check the question that you need, then you can answer those ones, or you can attempt to answer those kind of questions. Okay, so we have phasor addition. Sometimes it is necessary when studying sinusoids to add together two alternating wavefolds, for example, in AC series circuit that are not in phase with each other. Okay, so we're having this diagram representing the phasor additions of two phases. Okay, then we are having RCL circuits. We're having resistance, of which we spoke about resistance yesterday in electrotechniques, and 4, whereby we said the resistance of a circuit is just like it's a what can I say? It's we can just call it an instrument which resists the flow of current. So that's why you see sometimes whenever you're charging a phone, at the end of the day, the charger is hot or something. There are certain things or certain variables that are resisting the flow of current. So when the switch is closed, an AC voltage V is applied to the resistor R. This voltage will cause a current to flow, which in turn will rise and fall as the applied voltage rises and falls simultaneously. So I really need you guys to go and actually look at the RCL circuits, because they are also going to be part of examinations and also part of your test that I'm going to share with you guys. I think by next week, if I'm not mistaken. Okay. Then we have inductance. Inductors do not behave the same way as resistors, whereas resistors simply oppose the flow of electrons through them by dropping a voltage directly proportional to the current. Inductors oppose changes in current through them by dropping a voltage directly proportional to the rate of change of the current. Okay, so the inductance is represented by the letter L, and we are having a simple inductor circuit on Fig 1.15. Okay, so if we were to plot the current and voltage for this very simple circuit, it would look something like this. So when you are free, I would want you guys to go through all these notes, all these ones. Then you have capacitance. Then we said yesterday capacitors store energy, which is electrical energy. So I would also want you guys to actually go through these capacitance and capacitors. All right. Then we have impedance. Is the measure of the opposition that a circuit presents to the current when a voltage is applied. In the complex ratio of the voltage to the current in an alternating current AC circuit. Okay. Then we have the symbol of impedance is usually Z, and it may be represented by writing its magnitude and phase in the form of Z. Then we have the phasor angle. However, Cartesian complex numbers representation is often more powerful for circuit analysis purposes. Okay, so here we're having these kind of formulas that we're going to be using for impedance, depending on the kind of circuit that you are having. Okay, so Mr. Stella, I think you're the only one attending today. So this is very simple. The thing is that you just need to read it through. If you don't read it through, it's going to be very, very difficult. But if you just read it through and understand all these things very, very easily, I can promise you that this module, it's easier for you to actually get a distinction because it's very, very easy. It's the most easiest module. Industrial electronics and electrotechnics, those are the two easiest modules that you can get distinctions from. Okay. So we have power, we said we have phase angle with lagging and leading power factor. So we have these formulas that we need as well. Then we have power factor. The power factor is the ratio between the true power and the apparent power. So we're also gonna go through these things as well when we are doing Q&As. Okay. Then we have low power factor. Then we have series RCL circuit. Okay, so it's also having its own things. We have parallel RCL circuits. Then we have impedance of parallel. Then we have these kind of questions, applications. We have resonance. We have frequency effect. We have current at resonance. Then we have resonance frequency, resonance rise in voltage. Okay, then we have the quality of resonance, Q factor. All right, so we have Brandwich, and if I do parallel resonance circuit, so all these things, I need you to go through them up to this, which is the resonance frequency for a parallel LC circuit. Okay. Then when you are done, you can go through these equations, these activities. Then you do these checks here. Okay. When you're done with the checks, next week we are going to be starting from module 2, which is the direct current theory. Because of our time, next week I'm going to try by all means to cover at least 3 topics that day, because remember guys, you just needed a bit of what can I say, you needed an introduction to these things only. So the introduction I have given you from the AC current. So now I expect you guys to actually go home there and study ahead of everything. Then when you're having classes more, it's more of me answering the questions that you've found, or the questions that have come through, or things that you don't understand. Then we can do them in class, because the time is very, very short. Do you think this one is a 15-day course and you're supposed to know, I think, around 8 modules per subject? So that's going to be around 8 times 4, that's 32 modules in different subjects. Okay, so please, when you go home, try to do these questions, and if you have problems, then you can come, then we'll do them next week. Okay, so Mr. Sil, I don't know if you have any question from the module 1.
So far, I don't have any questions. So I think maybe from the here, I'll have to sit on my own and study these things with my own pace and my understanding. Then I think from there, that's when I'll have questions, actually.
Yeah, all right. So I don't want to waste much of your time. I know like you've been at work and tired. So we are going to end here. I'm not going to introduce chapter number 2. I was thinking that maybe I would introduce it, but I don't want to load you with a lot of things. So this is going to be it for tonight, and I'll see you guys tomorrow on engineering science and 4 as well.
Great.
All right, good night.
Thank you, sir. Thank you.